an element of n union t whole plus. So that means what? So context sensitive means this x should not be replaced by, rather this a on the left hand side should not be replaced by x all the times. When a comes between u1 and u2, only then this a should be replaced by x. That is the criteria for the context sensitive. That is based on the context. That is usually when in the example we saw that the verb goes, verb goes to 8. This is the rule actually. Wherever verb is present, we can replace the verb by the word 8. But here in the context sensitive, all the rules should be of this format. What is the format? Required format is U goes to V should be a production. What is the only condition is every replacement of the non-terminal on non-terminal present on the left hand side is based on the context. In this example, in this definition, we see that U1 A U2 derives U1 X U2. This gives a meaning that a will be replaced by x only when u1, u2 are present on both sides actually. So then coming to the discussion of context free, if each rule each rule of the production is of the form u goes to v and that u is an element of n. That means if the left hand side content of your u should be a single non-terminal. We don't worry about the content in the right hand side. This is called context-free grammar. In coming back to the regular grammar, every rule should be of the form u goes to v, and as told in the sense of context-free grammar, we have u an element in non-terminal, and the right hand side contents it may be exclusive at terminal. That is, v an element of t tells you that it can be a terminal or a terminal after that one non-terminal. For example, capital A goes to small a, capital A. Usually, terminals are represented by the small case letters, and non-terminals are represented or denoted using the capital case letter. So based on the template, based on the constraints, we classify the phrase structure grammar into four type of categories. First, length increasing, context sensitive, context free, and regular. And these four grammars generate the so-called languages. First, length increasing, recursively enumerable language, and the context sensitive grammar generates context sensitive language. Context free language generates context free grammar generates context free languages. Regular grammar generates regular languages. So having given the clear introduction, now we come to the illustration. Now we focus only on the context free grammar. Here, see this grammar. So whenever we want to express a grammar, we should provide these four components called n, t, p, s. Here, n is described as, n is with two symbols, s, comma, a. And t is having a description. The set t contains three symbols, a, b, c. So small a, small b, small c, they are terminals. Capital S and capital A, they are called non-terminals. Now the production rules are given like this. S goes to ASC, S goes to AAC, A capital AC, and the last production is A goes to small b. So for example, how to find out this? So given grammar, usually in this type of grammars, first given a grammar, we should be in a position to compute the language generated by the grammar. So one typical derivation in the grammar will be S derives ASC, the first production as such. After that, I am going to apply a production for S. There are two productions, rule number one, rule number two. They are, on the left hand side where they are having S. So I'll call this as S production. So now I want to replace here A and C. When the first rule, after applying the first rule, I have this S derives A S C. Here, small a, small c, they are terminals. There is no need for, we can't replace it further. So they are called terminals. Then capital S should be replaced again. For this, I can either apply the same rule 1 or another S rule is there, rule 2. So when I apply rule 2, when I apply rule 1 again, ASC, S is replaced by ASC again. So I will get AASCC. So before S, there are two A's, and after S, there are two C's. So now again, if I apply rule number 2, rule number 2 now, I am having S is replaced by small a, capital A, small c. So I am having triple A, capital A, triple C. So like then after that, I can apply the A rule, which ends with the termination A goes to small b. So I have this triple A, B, C, C, C. So now in generalizing this type of derivation, we will conclude that whatever, see, there are two S production. One S production, what does it do is it generates one small a on the left and it generates one small c on the right. And another S production does the same, does what, one small a on the left and small c on the right, but instead of S we have another non-terminal called capital A. So now, for every A, there will be a corresponding C in this phrase, in this word, the words generated by the grammar. Now, when we want to terminate, we apply the last rule, third rule, A goes to B. So now, if you see the pattern of the words generated, the number of A's on the left will be equal to the number of C's on the right, but there will be one extra b which comes in the middle, which is the which is because of the rule number 3, a goes to small b. So now with these three rules, repeated application of these three rules derives only these type of words of the format a power n, b, c power n, where n is greater than or equal to 1. So this is called the language generated by the grammar. Now coming to the another example. Now you are as told here in this example, what we did, what did we do here is, we were given the grammar, we were able to predict, we were able to compute the languages. Now here, given the language, can we design a grammar for it? Can we design a grammar which will generate this? So other so usually in theory of computing, either it is a generating device or a recognizing device. You will be given a language L and you have to design a device which accepts or which generates this. And the other way, you will be given device, and you have to compute the language generated or accepted by it. In that sense, we come to the second model of the problem. So given the language A power n, B power n, where n is greater than or equal to 1, and here we want to make it out, we have to find, we have to compute the grammar which generates this. So as told clearly, in the earlier grammar, if there is a, for example, see this, S goes to ASC. So whenever this production is applied, one A is getting generated on the left and one C is getting generated on the right. But here we want some generation in the sense there should be some, A should get generated on the left, at the same time B should get generated on the right. So in that sense, we write the rules S goes to ASB. Now in the earlier problem, for the termination purpose, we introduced a capital A in here. See here, the second rule, S goes to A, capital AC, and to terminate that, we introduced the rule A goes to B. In the same sense, ASB, that is, A gets generated to the left, B gets generated to the right. Now, to terminate, what I should do is, I have to have S goes to AB. I should not mention the rule number 2 as S goes to A or S goes to B. Because when the application of the rule number 1 will help you in generating as many A's on the right hand on the left hand side, which equaling the number of B's on the right hand side. So now what I do here is S goes to AB is the one which will terminate without affecting the number of A's and number of B's. They should be equal, because in fact the language given for our purpose is A power n, B power n. That is, this tells you that number of A's which comes sequentially on the left hand side should be equal to the number of B's which comes after the completion of all the A's. So in that sense, so with the common sense, we can easily derive, we can put the rules S goes to A, S, B, and another rule S goes to A, B. So now the sample derivation A, S, B. So every S will generate again A, S, B. So we'll have in the second step A, S, B, B. Then the third step triple A, S, triple B, like that. So now finally we can generate as many things. For example, if I want to generate one A and one B, that is AB, the mere application of rule number 2 is enough. If you want to apply AABB, you have to take the rule number 1 and apply rule number 2, then I will be getting AABB. If I want to have triple A, triple B, that is A power 3, B power 3. So first you have to have S goes to ASB, then again apply AASBB, then apply the rule number 2, S goes to AB. So this will give a clear picture about it. Now, if I want to, generate a grammar, if I want to design a grammar to generate all words with an equal number of A's and B's, there is a lot of difference between the earlier problem and this problem. In the earlier problem, all A's and on the number of A's and number of B's are equal. Here, the number of A's, number of B's can be in any position, whereas in the earlier problem, all A's came together, after that all B's came together. Here, for example, A, B, B, A, which will not be a valid word in the earlier example, because the language tells you very clearly A power n, B power n. So now I can't have this A, B, B, A. So now in that sense, this problem is slightly different. So it generates all words with an equal number of A's and B's. So for that, what we have here is, see this, we are categorizing this. First, whenever we generate small a, we have to ensure that one B is generated. See here, rule number 1, S goes to AB. What is it? What this rule will do? When one A is generated on the left hand side, we will have capital B. And finally, see the rule number 6, B goes to small b. So rule number 1 and rule number 6 tells you very clearly that number of A's and B's are kept same by the repeated application of rule number 1 and 6. But that of course that is not going to be the case alone. It can come at any place. For example, ABBA cannot be captured. ABBA cannot be captured by just the application of rule number 1 and rule number 6. So now what we do here is just observe that S goes to AB and B goes to BS again. So S goes to AB, B goes to BS, just to see the combined application of the rule number 1 and rule number 7.